maybe that means something to you. All right, so first order linear differential equation, well, first order differential equation, also known as linear, if it can be written in this form. All right, so a function multiplied by a derivative plus a function multiplied by another function of y is equal to another function, and the arbitrary function of x, a, b, and c. All right, so if you can get an equation to be to take on that particular form, then we would call it a linear differential equation. All right, so really what we're going to do is just at first practice getting it into the appropriate form, because once you do that, it becomes a lot easier to actually come up with the solution to the differential equation. Right, so this is the general form for a linear differential equation, but when it comes to actually finding the solution, we want to kind of take it another step. Or it is what it is, as Mr. McCallie would say. Or the exponent jumps over like a log like a frog, like Miss Hamilton would say. So anyway, I'm going to divide each part of this by the function a of x. And what we get is a new equivalent relation, and that is y prime plus b of x over a of x times y, poor quality y, times y equals c of x over a of x. All right, that coefficient function for y, we're going to call that a new function, p of x. All right, and the constant function, it's not really constant if it's a function, but it takes on the form of a constant. We're going to call that q of x. It's really a quotient function. All right, so because what we did was we created rational functions, potentially, assuming that these are polynomial in some capacity, not necessarily guaranteed. But if they were, then these would take on the form of rational functions. And so P and Q are typically what we would use, P, Q, and R to represent rational functions. Okay, so once you have your differential equation in the appropriate form, you could identify the P and Q, and that's all the problems on this page are asking us to do. So that's not too bad, right? So like in the first problem, all it's asking us to do really is just to get all the y's on the same side. So I'd have y prime plus 4y is equal to 3x. Whatever the coefficient function of y is, that's going to be your p of x. Whatever is all alone on the right-hand side, that's going to be your q of x. So sometimes it could be as easy as that. Really not much work to do. But then you see number 2, where you got a little bit more going on. So in that one, I would cross multiply first. 3xy prime is equal to 8y minus 6. But then once you do that, you could see, well, if we want to get the y's on the same side, I have like at least a little bit of a plan of attack here. I would just subtract the 8y from both sides. 3xy prime minus 8y is equal to negative 6. If you get your y's on the same side, the only thing in terms of an approach that you need to have in mind is that the y prime shouldn't have a coefficient function. Right? So I would just divide out the 3x from each part. And I'd be looking at y prime minus 8 over 3xy is equal to negative 6. Well, really it would be just negative 2 over x if you simplify. And so this whole shebang here is going to be your p of x. And this one over here, keep my coloring consistent, would be your q of x. All right, so far there's really not much to it because really, when you think about it, we haven't solved anything yet. I mean, we're trying to find y out of this, which is, you know, to see how that's going to happen from all this stuff is, you know, probably a little far-fetched at this point, but we'll get there. All right, so number 3, again, the goal is to get all the y's on the same side. So one step, and I can do that. So I'll just subtract the 3y prime. So I'll have negative 3y prime plus y is equal to negative 4x squared plus 5. Divide out the negative 3 from each part. I'll be looking at y prime minus 1/3 y is equal to all that stuff. I mean, you can clean it up if you want, but really isn't going to make much of a difference, at least until we see what the next step is all about. Once we do that, then you'll make a determination of what makes sense. All right, so my p of x is negative 1/3, and my q of x is this mess over here. Record on that. That whole left-hand side is a result of the product rule being carried out on this expression, x minus 2 times y. Really just play it out. If I were to take the derivative of this, it would be first times the derivative of the second, right? First, x minus 2 times the derivative of the second function y as a function of x would have a derivative that way. I would just have to denote as y prime or dy dx if I want, plus the second function y times the derivative of my first function, which would be what? 1. All right, derivative of x minus 2 is equal to 1. So that's what this is all equal to, all right? So what we're getting at from this idea here is that we already have a differential equation ready to rock and roll because this thing is equal to 3x squared plus 2x. Now, here's the big question, and it would be a question I would be asking, and I'm sure many of you are wondering. How the hell are we supposed to know that that's the result of the product rule on the left-hand side? All right, good question. The idea here is if you carry out steps 1, 2, and 3 in this process, what you will get as a result will be automatically the result of the product rule, right? So this guarantees that whatever is on the left-hand side of the equation will be the result of the product rule. And so then you could rewrite it like this. What is the benefit of doing that? Well, I can now solve this differential equation because I could swing my dx over and just rewrite this as this. So I'm separating my variables somewhat for the purpose of integrating. I'm integrating a derivative. What happens? Inverse operations, exactly. So I'm just left with an x minus 2 times y. On the right-hand side, it's x cubed plus x squared plus c. And so I would get my final answer if I'm looking to solve for y in terms of x cubed plus x squared plus c all over x minus 2. All right. So if you can guarantee that the left-hand side is the result of the product rule, you can write it as the derivative problem that it was prior to its expansion, and then just work backwards from there. All right, so in the next problem, I'm going to show you how to guarantee that the left-hand side is the result of the product rule so that you can carry out this process. Right? It's a pretty cool procedure. All right, also involves, this one involves an initial value, but as you know, is not the challenging part about all of this stuff, because that's just plug and shut. All right. So we're in the appropriate form. All right, that's the standard form for a linear differential equation. I can easily identify my p of x and my q of x, but we really don't need the q of x. So I'm not even going to note it. What I want to figure out is mu of x is equal to e to the integral of p of x dx. So mu of x is e to the integral of -2 dx. No plus c's in intermediate steps. Plus c's happen at the very end. Right? So the antiderivative of -2 dx would be what? -2x. So we have e to the -2x. All right, so what I'm going to do is take my original differential equation, y prime minus 2y equals 4x plus 3, and multiply that by e to the -2x. All right, so multiply each part of it by that. So we're looking at e to the -2x y plus 2 e to the -2x y. Oh, sorry, y prime to start. This one is a y. Actually, still minus. I was looking at the wrong negative. Then 4x e to the -2x plus 3e to the -2x. All right. It looks like the situation got much worse, but if you carried out the process correctly, the left-hand side is the result of the power rule, product rule. It's just a matter of picking out that product rule. So the good news is you really only have to work off of the first thing, the first term of your expansion, because if you're just kind of saying the product rule out loud to yourself, well, I guess during the group test you can say it out loud. It should be the first function multiplied by the derivative of the second. All right, so the first function is e to the -2x. Multiplied by the derivative of the second function. So what's my second function? Just a y. All right, because that is the derivative of my second function. So the derivative of y is here, meaning it was the derivative of whatever the second function was, and it must have been y in that circumstance. Right? So how do we verify that that is in fact correct? All right, well, we got first multiplied by the derivative of the second. Okay, so now find plus the second function times the derivative of the first. What's the derivative of e to the -2x? -2e to the -2x. All right, so it checks out. So we do know that the left-hand side is, in fact, the result of the product rule, for particularly e to the -2x times y. All right, so we clean it up. We have the derivative, e to the -2x, e to the -2x, 3e to the -2x dx. Integrate both sides. Inverse operations on the left. On the right, though, we have some work to do. looking at you, 4x e to the negative 2x. The other one's not bad. Not worried about the 3. Yep. Integration by parts. Alright, so left-hand side cancels. The integral and the derivative cancel out, so that's fine. The right-hand side, we know we can figure this one out easily enough. It's this one. You need integration by parts to figure it out. Alright, so we'll establish a u and a dv. What's my u? 4x, my dv? E to the negative 2x dx. So du, bless you, equals 4 dx. V would be equal to negative 1/2 e to the negative 2x. So we just need a little uv minus the integral of v to u action. So 4x multiplied by negative 1/2 e to the negative 2x minus the integral of v du. So minus the integral of negative 1/2 e to the negative 2x times 4 dx. Ugh. I mean, it cleans up kind of nicely. So we're looking at negative 2x e to the negative 2x plus the integral of 2e to the negative 2x dx. We just can't lose sight of everything else, because this is just the integral of 4x e to the negative 2x dx. But this part's almost done, so that's good news. So negative 2x e to the negative 2x. And it's going to be minus e to the negative 2x. All right, so now I can tackle the other guy. So this guy over here, I'm going to bring that down. Fortunately, it's the same technique. So e to the negative 2x, but I'm going to divide by the negative 2, so minus 3/2 e to the negative 2x. So that's this guy coming right on down here. And the whole thing is equal to e to the negative 2x y. Now, somewhat shockingly, we have a cancellation, but we don't want to do any cancellations yet because I haven't added the plus c. But this is something you got to be careful about, because the temptation is there. You see those e to the negative 2x's across the board, and you want to just go after it like an animal, you know. But there is a plus c there, so it's not a clean sweep. So you can divide out the e to the negative 2x, and you must to get y alone, but you're still going to have an e to the negative 2x in there somewhere, particularly associated with the c at the end. All right, so y would be equal to negative 2x minus 1 minus 3/2, which we can consolidate in a second, plus, well, if I'm dividing c by e to the negative 2x, that's the same as multiplying it by e to the 2x. So c e to the 2x. All right, and so the general solution would be negative 2x minus 5/2, like terms, plus c e to the 2x power. Now there was a condition, we'll take that in a second, but look at that. But it's funny though. I mean, okay, there's nothing funny about it, but it's interesting. Okay, maybe not that either. The idea that all of this stuff had nothing to do with the new material, it's something. Because really, this is where the new stuff really ended. Right? Going from here to here, really. After that, it's, okay, I needed to know that this is a legal move. But then after that, it's all stuff from prior knowledge. Right? So it's the introduction, but you know that, even from homogeneous differential equations. It's nothing new to you, where you've seen all this happen before. You have the one little step in there that's the new material, and then everything else is related to stuff that you had to know from before. Most often pre-calc, you know, that friggin' course, man, pre-calc.
Does the y c?
We're gonna apply that now. So y of 0 is equal to -2. Honestly, I mean, in reality, pre-calc should probably be like a 2-year course. But then nobody would get to calculus in high school. So that's why it's probably not that. But I think most people agree, at least to some extent, that when you screw up a problem in this class, very rarely does it have to do with the calculus. It's almost always the pre-calc. All right, so solving for C, I'm adding 2.5 to both sides, really, so we're looking at C is equal to 1/2. So, final answer, y is equal to -2x minus 5/2 plus 1/2 e to the 2x power. Now, in theory, you should be able to differentiate this and come up with that, the original problem that you were given, the original differential equation. The thing is, it's very hard to bring yourself to do that after doing like a 1.5 pages worth of work. I don't have a landing to put this on. So therein lies the problem. You want to, but you also don't want to at the same time.